Welcome to your fourth integration lesson, integration 4, which is the definite integral. What's important to understand here, just as we mentioned the definite integral, is that everything that you've been doing in the first 3 integration lessons was finding the indefinite integral. And even when you found C, it was still the indefinite integral. The indefinite integral is basically just performing the integration rules, finding the integral of different functions. All right, and now today we are going to actually start finding the definite integral. And you will see that, as is shown on the first slide here, that the application of definite integral is actually area under the curve, even though in today's lesson we won't quite get into finding area under curve. Today we're just going to perform finding the definite integral. We're going to show how to find the definite integral. All right. So first of all, just a definition. Again, as you've hopefully found, that indefinite integrals are just a family of functions that all differ by the same constant. That's to say, if you took the integral of x squared, for example, obviously that integral is x cubed over 3 plus c. And again, there could be many c's, and they would all come from the same function, x squared. All right? So the fundamental theorem of calculus, again, lots of words, but really what it's saying is on a continuous function, so that means a function with no breaks, okay, between 2 intervals, or between 2 points, a and b, all right? And if f is the integral of a function small f, then the definite integral can be found by putting the boundaries, the low boundary a to the upper boundary b, okay? Substituting those, again there, into the function capital F of x to get f of b minus f of a. There's a lot of words, and it's a lot wordier than the solution really is, all right? Anyway, this line is read as the integral of f of x with respect to x from a to b is equal to capital F of b minus capital F of a. And again, the picture in the orange box below actually shows what you're finding when you find that integral. You're finding the area under the curve, or in other words, between the curve and the x-axis, between 2 boundary values, a and b, on the x-axis. Okay. All right, so again, a lot of theory there, but you'll see how it gets put into practice. All right, so here's the steps basically for finding the definite integral. First, you're going to find the indefinite integral as we have been the last 3 lessons using the rules that we've been using. You'll write your result as capital F of x, and then with the boundaries a to b, and then simply substitute in those a and b values. Substitute in your upper boundary value first into f, and then subtract, substituting in the lower boundary a. Okay, so here's how it'll look. So like we said, we're first going to just perform the integration as we have been. So the integral of 1 over x, again, hopefully everybody's comfortable and knows that now. That should just be ln x. And now we'll put the boundaries of integration onto the square brackets. Usually it goes lower on the bottom, upper on the top. Okay, it seems obvious. And now we do the substitution. So we substitute in the upper boundary value, so we get ln 5, and we substitute in the lower boundary value for ln 3. And now what we have is we have subtraction of logs, which if you still want to apply some log properties, you can make into ln 5 over 3 for a nice, concise answer. Maybe in an IB question they might ask, give your answer in the form ln a over b, so you would have to know how to do that. But basically, right there, those are the steps to find the definite integral. It's that easy. Obviously, the functions can get more involved, a little bit more complicated, but for the most part, it is this easy. So we'll try with these functions. All right. So the first one, again, we have a a combined function x minus e to the negative x dx. Again, what I would probably do here is I'd probably separate the two functions, which you're allowed to do using your sum and difference rule. All the rules that we've learned up until now still hold true, all right? So I'd do like this, minus the integral from negative 2 to 0 of e to the negative x dx. And now just perform each of these integrals again, and now you're going to put into square brackets. So now we have x squared over 2, the integral of x, right, from negative 2 to 0. And then we're going to subtract the integral of e to the negative x. Now the integral of e to the negative x, again, is itself. So e to the negative x. But we also have to remember to divide by negative 1, so that's going to become positive. And then we'll put our square brackets on. And we put our boundaries negative 2 and 0. So now into the first set of square brackets, I should put equals here. Into the first set of square brackets, I'm going to substitute 0 first. So we get 0 squared over 2. And then I'll subtract and then substitute in negative 2 squared over 2. And then the second set of brackets is the same thing. We substitute in our upper boundary, so e to the negative 0 minus e to the negative of negative 2. And our final, next step of our answer, the first term in the square brackets is just going to be 0, and it's going to be negative 4 over 2, right? And then in the second set of brackets, it becomes plus, we put negative e squared, which we can write as a final answer of negative 2 minus e squared. And that would be your final answer, the definite integral. Well, I guess I should have mentioned earlier too that your definite integral is always a number. It was mentioned earlier in the notes, I didn't highlight it though. But your definite integral is always a number. You're getting a number answer. All right, the next question with the sign in it. So again, we're first going to perform the integration. Again, you should be able to integrate functions of this form. So the integral of sine 3x, you should know is negative cos 3x. And again, because 3x is linear, we need to divide by the coefficient of x in front. And then we put on our boundaries of integration, pi over 6, pi over 2, like that, lower and upper. And now we can substitute in our values. One thing that we can do here, it's a property that I'll show you on the next slide actually, but you can take out any constant. So it's worthwhile to probably factor out the negative 1/3 and then do the substitutions just into the cos part of the function. So cos, and then 3 times pi over 2 minus cos, and it's 3 times pi over 6. So this now leaves negative 1/3. The value of cos 3 pi over 2, then you have to recall some of your trig. Cos of 3 pi over 2 is actually 0. It's the x value at 3 pi over 2. And cos 3 pi over 6, that's actually the same as cos of pi over 2, which is also on the y-axis, and we want the x coordinate at that point, so that's 0. And so this whole integral ends up having a value of 0. And for right now, you may not understand why that happens, but in the next lesson, you'll get the significance of that. All right? So on this page, we just have some properties, which we'll go over. So the first one again is the constant multiple rule, okay? And I've used it already. It allows you to take the constant in front of the integral and then perform the integration, and the boundaries of integration stay on the exact same. The second one is your sum and difference rule, which again we've used or we've seen before when we did the indefinite integral, but it also holds true. And again, you just apply the boundaries on each part of the integral that you do. Number 3 is a unique property for the definite integral. All it's saying is if your lower and upper boundary are the same, the answer for the integral must be 0. Again, if you think of it in terms of accumulated area between your upper and lower boundary, obviously if your boundary is a line, there is no accumulated area, so that's why the answer is 0. Also, number 4 is unique for definite integrals. What it's saying is, normally we go lower boundary to upper boundary, so A would be smaller than B. But if you flip the order of A and B, all right, what it does is that actually makes the value of your definite integral opposite. Okay, so given a certain order of boundaries, if you flip the order of the boundaries, you get the opposite sign answer for the definite integral. All right, and what property number 5 is saying is if you're integrating over an interval between A to B, you can break the interval up yourself, and again, later on, there will be some advantage to doing this. So let's say we have some curve like this, and we have our boundaries, see here, A, and we have a boundary here, B, okay? What I can do is I can choose to put in an extra boundary, say in the middle, say right here, and I call that C. And now what I can do is I can integrate from A to C, which is what's shown here. This is the integral from A to C, and then we can integrate, which would give me this area under the curve. And then I can also integrate from C to B. Show that. I can integrate from C to B, which would give me that part of the area under the curve. All right, so you'll see later on that there is some advantage to being able to do that. For right now, it doesn't really matter. All right, and then the last slide here, I'll do a couple of these examples for you, maybe leave you one to try on your own. So again, this is symbolic integration, but it's integration involving using the properties. All right. So the first question here involves sum and difference. So what I would do is I would break it apart, write each integral separately. Make sure you include dx with each part. That's necessary. Okay, like this. And now I might even use the constant multiple rule in the first case. All right. And now we can do our substitutions because we know the values of these. So integral 1 to 3 f of x dx is 2. So this is 3 times negative 2 minus, and the integral from 1 to 3 of g of x dx from above is 3. So here my answer is negative 6 minus 3 for negative 9. I'll just do the other one, the second one here, just quickly. Again, break it apart. So go from 5 to 1, f of x dx minus integral 5 to 1 g of x dx. All right. And now this is where the order of the boundaries comes in. In the givens above, the boundaries are in the order 1 to 5. So we need to, that's the only information that we know, so we need to have our boundaries in the other order. And again, the property says if we flip the boundaries, we change the sign of the integral. So now, if I change it from 1 to 5, it becomes the negative of this, f of x dx, and obviously the negative of the second one as well, which now becomes positive. Okay, and now we can substitute in our values. This is negative of 7 plus 5, and our final answer then would be negative 2. All right, I'll leave the third one for you to try on your own. Just one question I'll put in your mind, and we'll maybe talk about it in class. But if you notice, with the definite integral, we have not included c in any of our integrations. I want you to think about why we have not included c, and see if you can come up with an answer for me. That's it for now. Thanks.